Infinite energy revealed. Scientists cracked fusion energy and created a mini-sun. The race to harness the power of the stars has reached a turning point. After decades of being just 30 years away, fusion energy has finally crossed a threshold that changes everything we thought we knew about our energy future. Scientists have achieved what many thought impossible, creating and containing miniature suns here on Earth that produce more energy than they consume. This isn't science fiction. It's happening now, and it could revolutionize our world in ways we're only beginning to comprehend. The breakthrough that changed everything. Imagine a world where energy is clean, abundant, and virtually limitless, where a single gram of fuel contains the energy equivalent of 11 tons of coal, without producing greenhouse gases or long-lived radioactive waste 47. This is the promise of fusion energy, and recent breakthroughs have brought us closer than ever to making it a reality. In a historic achievement, Lawrence Livermore National Laboratory's National Ignition Facility, NIF, has successfully demonstrated fusion ignition multiple times since 2008 December 2022. By firing the world's most powerful lasers at a tiny fuel pellet smaller than a pea, scientists created conditions more extreme than those at the core of our Sun 13. For the first time in human history, this experiment produced more energy than was used to initiate it, a scientific milestone that many experts believed might never happen. But this was just the beginning. In October 2023, NIF set a new record, firing 2.2 megajoules (MJ) of laser energy at an ignition target, resulting in 3.4 MJ of fusion energy yield 8. Even more impressive, in July 2023, a previous experiment using 2.05 MJ of laser energy produced a staggering 3.88 megajoules of fusion energy, the highest yield achieved to date 38. But wait, if we've already achieved fusion that produces more energy than it consumes, why aren't we powering our homes with it yet? The race to contain a star. The core challenge of fusion isn't just creating the reaction, it's containing it. Think about what we're trying to do: control a miniature star. At temperatures exceeding 100 million degrees Celsius, that's over 5 times hotter than the Sun's core, no material on Earth can directly touch the superheated plasma without instantly vaporizing 24. Scientists have developed 2 primary approaches to this seemingly impossible task. Inertial confinement, the power of light. The NIF approach uses the world's most powerful laser system to compress and heat a tiny fuel pellet from all directions simultaneously. For a fraction of a second, the fuel implodes, creating pressures and temperatures sufficient for fusion to occur. This approach has proven that fusion ignition is possible, but sustaining the reaction remains the next frontier. 23. Magnetic confinement, caging lightning. The second approach uses powerful magnetic fields to contain and control the superheated plasma. Like capturing lightning in a bottle, these magnetic fields keep the plasma suspended away from the reactor walls. China's experimental advanced superconducting tokamak East reactor, nicknamed the Artificial Sun, recently shattered records by maintaining a stable fusion reaction at 100 million degrees Celsius for an astonishing 1,066 seconds. That's over 17 minutes of containing a star. Not to be outdone, French scientists at the West reactor have pushed the boundaries even further, maintaining plasma for more than 22 minutes 7. Each advance brings us closer to the Holy Grail, a self-sustaining fusion reaction that can power our world. Think about this for a moment. We're literally bottling starlight. The same process that has powered our sun for billions of years is now being recreated and controlled in laboratories around the world. The global race for infinite energy. The quest for fusion has ignited a global competition reminiscent of the space race. Nations and private companies are investing billions, knowing that whoever masters fusion first will hold the key to humanity's energy future. China has made extraordinary advances with its East reactor, demonstrating unprecedented stability in fusion reactions. 9. The United States continues to break records with the NIF facility, achieving the critical 300 megajoules per square meter milestone of fusion ignition. 8. France hosts the largest international collaboration in the field, the International Thermonuclear Experimental Reactor ITER. though recent delays have pushed its full operations back to 2039-5. Meanwhile, private companies are challenging the notion that fusion requires massive government projects and decades of waiting. One fusion research company, Helion Energy, boldly claims to be on track to have the first ever commercially operating fusion plant in 2028-5. Others, like Tokamak Energy, are pursuing their own accelerated timelines. Overcoming the impossible engineering challenges, creating a functioning fusion reactor isn't just a physics problem. It's an engineering marathon that pushes materials science to its absolute limits. The materials used must withstand temperatures hotter than the sun, intense neutron radiation, and enormous magnetic fields, all while remaining operational for years 26. Consider the challenge of heat. At fusion temperatures, plasma becomes a fourth state of matter that would instantly vaporize any conventional material it touches. Engineers must design systems that can safely contain this plasma while extracting the tremendous heat it generates to produce electricity for. Then there's the fuel problem. While hydrogen is abundant, the specific isotopes needed for the most efficient fusion reactions, deuterium and tritium, require specialized production methods. Tritium is particularly challenging, as it's rare and radioactive with a half-life of just 12.3 years, requiring on-site production in future commercial reactors 6. Imagine building a device that can withstand the conditions at the center of a star, day after day, year after year, without failing. This is the engineering challenge that has made fusion so elusive, until now, from science fiction to reality, the timeline to fusion power. The persistent joke among scientists has been that fusion is always 30 years away, a testament to how the goal seemed to perpetually recede as new challenges emerged. But that joke is no longer accurate. We've crossed critical scientific thresholds, and the remaining challenges are primarily engineering and economic, rather than fundamental physics questions. 15. Some private fusion companies are making bold predictions. Helion Energy claims they'll have a commercial fusion plant operational by 2028, while others suggest the early 2030 is a realistic timeframe. 5. Government-backed projects tend to be more conservative, with projections extending into the 2040 and 2050. The actual timeline will likely depend on funding, political will, and whether we see additional breakthrough innovations in the coming years. What's clear is that we're no longer asking if fusion power will work. We're asking when it will power our grids. Consider this: someone alive today will be the first human to flip a switch and use electricity generated by a fusion power plant. That person might even be you. How will that moment change our relationship with energy forever? The promise: what fusion means for humanity. If successfully harnessed, fusion energy would represent the most significant energy breakthrough since humans first controlled fire. The potential benefits are staggering. Near limitless clean energy. 1 gram of fusion fuel contains the energy equivalent of 11 tons of coal without producing greenhouse gases. 47. No long-lived radioactive waste. Unlike nuclear fission, fusion doesn't create long-lived radioactive waste that requires storage for thousands of years. 67. Enhanced energy security. The primary fuels for fusion, isotopes of hydrogen, can be derived from seawater and other abundant sources, making energy independence possible for nations worldwide. Space exploration. Beyond Earth, fusion could revolutionize space travel, potentially enabling journeys to Mars in weeks rather than months, and opening up the outer solar system for exploration. 1. Economic transformation. With abundant energy, costs for manufacturing, transportation, water desalination, and countless other energy-intensive processes would plummet. But here's something to consider. Are we prepared for a world of energy abundance? How would unlimited clean energy reshape our societies, economies, and relationship with our planet? The final challenges. From laboratory to power grid. Despite the extraordinary progress, several hurdles remain before fusion powers our homes. Scientists and engineers must still scale up energy production. Current experiments produce energy for fractions of a second or minutes. Commercial plants need to operate continuously for years. 4. Improve efficiency. Even with recent breakthroughs, the total system efficiency needs improvement. The lasers at NEF, for example, require much more electricity to operate than the fusion reaction currently produces. 3. Develop materials. New materials must be engineered to withstand the extreme conditions inside fusion reactors for extended periods. 26. Reduce costs. The economics must work. Fusion plants need to produce electricity at costs competitive with other energy sources. 56. Build the infrastructure. Ultimately, we need to construct an entirely new energy infrastructure around fusion technology. The competition, nations racing for fusion dominance. The fusion race has intensified as nations recognize its strategic importance. China's recent achievements with the East Reactor have demonstrated their commitment to becoming a fusion leader. 49. The United States continues to push boundaries with the NIF facility and supports various private ventures. 8. The European Union, along with partners including Japan, India, Russia, and South Korea, backs the massive ITER project in France. 9. This competitive landscape accelerates progress, but also raises questions about cooperation and knowledge sharing. Will fusion technology be dominated by a single nation or company, or will it develop as a shared human achievement? Think about the geopolitical implications. How would the world change if one country achieved commercial fusion years ahead of others? Would they share this technology or use it as leverage in international relations? The final frontier. Are we ready? As we stand on the threshold of a potential energy revolution, we must ask, are we ready for fusion? Not just technically, but as a society. The transition to fusion power would represent a fundamental shift in our relationship with energy, from one of scarcity and environmental compromise to one of abundance and sustainability. This transformation would ripple through every aspect of our civilization, from economics and geopolitics to our very relationship with our planet. Perhaps the most important question isn't when fusion will arrive, but what we'll do with it when it does. Will we use this star power to heal our climate, lift billions from energy poverty, and propel humanity to new frontiers? Or will old patterns of inequality and short-term thinking limit its transformative potential? The science is nearly there, the engineering is progressing rapidly, but our wisdom and foresight will ultimately determine whether fusion fulfills its promise as humanity's clean energy salvation. One thing is certain, the power of the stars will soon be in our hands. What we do with it will define our future. As we harness the power that drives the cosmos, we must ask ourselves, are we wise enough to wield the fire of the stars?